energy storage comes in a huge variety of types and sizes. And this quickly becomes a challenge of its own. If you have a number of batteries at your disposal, which one do you charge first? Which one do you discharge first? Does it matter? Well, in the most general case, these are not easy questions, and often there are no easy answers either. So in this video, I will provide examples of cases where coordination of storage units is required. Then I will describe the special case where we use storage units to discharge, for example to protect the power system from a blackout. In that case, there is an intuitive algorithm that has been shown to be optimal. And finally, I explain how charging, an essential feature of energy storage, complicates everything. Let me start by introducing this illustrative example. We consider a neighborhood with a shared battery system. This includes a large battery with a discharge power of 1 megawatt and a usable storage capacity of 500 kilowatt hour. So that means it can run at a maximum power for 30 minutes if we assume it's fully charged. In addition, individual homes have local battery storage systems. These are much smaller, with a discharge power envelope of 5 kilowatts and a usable storage capacity of 10 kilowatt hours. And this gives these batteries an effective duration of 2 hours. So a question we might ask is the following. If we had total control over all these batteries, how should we coordinate their usage? Well, in one scenario we can give a single satisfactory answer to this question. Luckily, that's a fairly common scenario, when the batteries are tasked with supporting the system in a stress situation. So the aim is to minimize energy shortages, and there is no possibility to charge during the stress situation. So taking this neighborhood battery example, we can represent the batteries as follows, where the width of each rectangle represents the maximum discharge power, and its height, the duration. In this case, the area of each rectangle represents its storage capacity, measured in kilowatt hours. Now note that these horizontal dimensions are not drawn to scale in this image. So next we consider how to use these batteries to satisfy a power demand pattern that we do not know in advance. And we will draw this curve on the right as it happens. So for this situation, there is an optimal policy that coordinates the power draw of the different batteries, which is called the greatest discharge duration first policy. I will explain that policy briefly. So let us suppose that at first, the batteries are asked to supply a moderate power level. Well, we start using the batteries with the greatest remaining discharge duration, which are the home batteries. The load isn't that high, so the home batteries can fully supply the load, and their energy levels will deplete over time. Next, the requested power level rises steeply to the point where the home batteries cannot supply enough power. So the home batteries run at maximum power and the neighborhood battery joins in. The remaining storage duration for all batteries reduces. Now, when the power consumption decreases again, the home batteries can again supply all power. And since they still have the greatest discharge duration, they share the load equally. That is, until they reach the remaining discharge duration of the neighborhood battery. From this time onwards, all batteries will share the load proportionally, so that their discharge durations remain equal as they decrease. Now this, in a nutshell, is the greatest discharge duration first policy. You can prove that this is the best policy for supporting the system if you consider batteries that can only discharge. And even better, it's a greedy policy, so you do not need to forecast the future to use it. Now, if you're interested in more details, please see the paper linked below. Unfortunately, such simple solutions vanish when you need to consider both charging and discharging. And I should clarify that because all batteries clearly do charge some of the time. But what I mean are cases where there are limits on charging, such as how much time or how much energy you have for recharging, so that this may affect your ability to discharge. There are a few specific examples worth mentioning. All practical energy storage solutions have some losses, so resulting in an efficiency that is less than 100%. If energy supplies for charging are limited, we should carefully choose which storage system to charge first, as the most efficient battery may not be the most flexible for discharging. And second, a special case of the same problem occurs even if you cannot charge externally. It's sometimes desirable to transfer energy from one battery to another in order to even out the energy stored across batteries and prepare for high demand peaks. However, you inevitably incur losses, so you need to wonder whether the increased peak readiness is worth the energy losses. And finally, you face a different set of complications when the amount of time you have for charging is limited. So take this example with two batteries with the same specifications that are used together in an electric vehicle. If they both need an equal amount of charge, we can charge them both at their maximum rate until they both hit their maximum capacity. In other words, they are perfectly set up for smart, fast charging. On the other hand, if these two batteries require unequal amounts of energy, then the one that starts out with more energy at the beginning of the session will quickly reach its full capacity. And at this point, the maximum charge rate will drop to that of the single battery that is still charging. As a result, charging both batteries to full capacity will take longer. So these examples indicate that there are many subtleties involved in the coordination of charging and discharging in sets of batteries, or storage units more generally. These become especially pronounced when you are faced with uncertainty. Uncertainty about what will be asked of aggregate storage facilities, or how much time and energy there will be available for recharging. So for this reason, this is very much an active research frontier. And it's an important one, because solutions to this problem would allow us to make progress towards a number of important applications. You have already seen a first example of a community storage system that can mix home batteries, large centralized batteries, and any number of electric vehicle batteries. A second important example is the provision of services using decentralized batteries. Aggregators can collect the flexibility of hundreds, thousands, or potentially millions of storage devices and use them to offer services. And to do so, they have to encode the potential of these distributed devices into products, such as this virtual battery. And vice versa, the services offered using the virtual battery must be translated back into commands for the individual batteries. And a very different challenge arises in the planning of future energy systems. It is clear that storage will need to play an important role in the system to deal with the variability of renewable resources. But there are many types of storage, from small and efficient flywheels to inefficient, high-volume hydrogen storage via electrolysis. So it's not at all clear how the various storage resources should be coordinated for high efficiency and robustness. So I've ended this video with 3 important use cases that require the coordination of storage resources: community storage, aggregation and disaggregation of storage, and the interaction between short-term and long-term storage, especially important for planning the energy transition. Now, in the discharge-only case, the greedy greatest discharge duration first policy provides a solution that's optimal in terms of system robustness. However, complications quickly pile up when we allow for charging in less than optimal conditions, and that is with limited time or energy. And specific complicating factors include the different efficiency losses between batteries, the subtle impacts of cross-charging between batteries, and optimizing batteries for fast charging, which can interfere with other goals.